Just going to walk through the properties of vector addition and scalar multiplication on page 431 really quickly. All of these are really intuitive based on all of the rules you already know about addition and multiplication for real numbers. So, vector addition is commutative, meaning that vector u plus vector v is the same as adding v plus u, right? So commutative. And scalar multiplication, meaning multiplying by a non-vector number, so like the number 5, is also commutative, meaning that if you do 5 times vector v, it's the same as doing vector v times the number 5. Again, this is not vector times vector. We have not dealt with vector multiplication yet. Right now we're multiplying only by numbers. Both of these properties both of these actions are also associative, meaning that you can group them differently, right? So associative means that if I'm adding 3 vectors, u plus v plus w, I could either add u plus v first and then add w, meaning I associate u plus v together first and then add w, or I could have done v plus w first and then added u after the fact. Associative. Also, multiplying by a scalar is associative. If I have two scalars, c and d, times a vector v, I could either do c times the quantity vector v times d, meaning I did this multiplication first and then c, or I could have done c times d first and then multiplied the whole thing by vector v. Distributive, if I have a constant or a scalar in front of the sum of two vectors, I could distribute that multiplication so that I'd get c times the first vector plus c times the second vector. Similarly, if I have a single vector times a sum of two scalars, I could, instead of combining the scalars first, just distribute the vector and make it c times the vector plus d times the vector. The identity property, which just says that there exists some element that you can add to the vector to mean that nothing changes at all. In this case, it's the 0 vector. So the additive identity in vectors is the 0 vector, just like the additive identity in numbers is 0. So if you add 0 to something, it does not change. So vector u plus the 0 vector would just give you vector u again. And also the multiplicative identity, which in terms of scalar multiplication is 1. So if I multiply the number 1 times vector u, I still get vector u. Nothing changes because, again, the multiplicative identity is 1. And then inverses in the sense that if you add vector u to the opposite of vector u, you get the 0 vector or the identity element. So those are our, and in this situation there is no inverse for multiplication because notice that if I were trying to solve for the 1 here, I would have to be dividing by a vector, and that does not fit scalar multiplication as an operation, so it doesn't exist in this situation, like in this set of rules. All right.